In the generation of electricity, the importance of magnetism cannot be overemphasized. In the 18th century, Michael Faraday was able to prove it using magnetism. At that time, he was able to deflect the needle of a galvanometer momentarily using this method. However, in the following year, which is the year 1832, Joseph Henry discovered the phenomenon of self-inductance and mutual inductance independently. During his magnetic research, Henry decided to experiment with how electromagnets could be used to lift items. And he was credited greatly for improving the design at that time. Firstly, he devised a means of insulating the wire to be used. Because at that time, insulated wire for electrical use was not commercially available. So in order to have a large number of tight turns, Henry insulated the wire itself with silk thread. This makes it possible for the length of the wire to be formed into coils. And to further prevent short-circuiting of the windings, he varnished the iron core and separated the turns of wire to keep them from touching each other.
Now when the coils are connected to a voltage source, the source we are talking about here is a battery. Because as at that time, batteries were the primary means of electricity generation. Electricity generation via magnetism is at the infant stage at that time. When powered on, the coils generate a force that is only able to lift a metallic material that is lightweight. After this, Henry decided to add more coils which are further connected to the coils. When powered on, Henry noticed that the lifting power was greatly increased, almost by 21 times the lifting force of the force experienced the last time. He further added more windings again, and also, the added winding was further connected to a battery source. He noticed again that there was also a significant increase in force experienced over the last experiment. So Henry realized that, by using more wire, he was able to create greater magnetic field strength.
Quickly he wrote a paper describing these experiments and his electromagnetic winding principle. He sent it off to Benjamin Silliman, professor of chemistry and natural history at Yale College and editor of the American Journal of Science. Henry became well known for the powerful electromagnets he constructed, and often demonstrated them before large crowds. An electromagnetic he built at the behest of Yale College was able to lift more than 2,000 pounds of weight. This was a very impressive feat at the time. Later Henry electromagnets were capable of suspending in excess of 3,500 pounds of weight.
However, because Henry was a persistent builder of electromagnets and as such, he was not completely satisfied with what he had built. So he built larger models with better windings, and he conceived of new applications such as the doorbell and magnetic relay, which Samuel Morse adapted to create his revolutionary telegraph. It was then that he discovered the phenomenon of induced currents of a conductor on itself, which was later termed self-inductance. In his experiments, he discovered that, when a copper wire not more than a foot in length is connected to a battery source, when it is either formed or broken, no spark is perceived. But if a wire of 30 or 40 feet long is to be used instead of the earlier short wire used, although no spark will be perceptible when the connection is made. However, when it is broken by drawing one end of the wire from the battery source, a vivid spark is produced. He discovered again that, if the rating of the battery is high enough, a spark can also be given by the short wire also.
Using this method of measurement, Joseph Henry discovered that uniformly coiled copper wire exhibits a stronger self-inductance than straight wire of the same total length. Joseph Henry used numerous copper helices of varying lengths and thicknesses to prove this. It is on this note that Henry makes a publication in the year 1832. That the self-inductance of a material is the response of a material to the changing magnetic field which is caused by either the interruption or resumption of electron flow within the conductor. And the strength of this property is dependent upon various factors such as the resistance and the arrangement of the conductor. This statement was presented to be published in the October edition of the American Journal of Science that year.
So practically, in order to fully understand how self-inductance truly works, we have a setup here that is connected to a bulb here. Now when I flick this switch to the on position, the bulb will instantly glow, which is an indication that current is flowing from the battery to the bulb via the wires. Now, when a coil of many turns is connected in series with the bulb, and when the switch is flicked to the on position, unlike before, the bulb will begin to slowly glow until it reaches its maximum. Likewise, when the switch is flicked to the off position, the bulb also gradually glows dimly until it stops glowing. So what really happened is that, as current flows through the circuit, it gradually induces a magnetic field in the coils. Now, the created magnetic field will also induce its own current in the circuit, which will flow in the other direction, thereby impeding the flow of the source current.
Again, it is important to note that when the initial current is increased, the induced current also increases also. And is a result of this that there are delays in how the bulbs glow when powered on and off. It is also important to note the differences between these terms, which are induction and inductance. Induction is the process of producing an electromotive force due to a changing magnetic field, while inductance is the property of a conductor that opposes changes in current flow.
This phenomenon can be proven using these mathematical expressions. Looking at that coil there, which contains n number of turns within, epsilon is equal to minus L, di, and over dt, where L is called the inductance, which is also measured in Henry. With this, we can now be able to describe the behavior of this passive element within a circuit, which is also known as an inductor.
Out of curiosity, Henry also brought another coil near the first coil. And he observed that, although the magnetic flux tends to produce a self-inducting current which impedes the flow of current from the source, the magnetic flux also induces a magnetic flux which causes current to flow in the other coil. This behavior is what is known as mutual inductance.
Although Joseph Henry proved this independently, Michael Faraday was given the credit because he was the one who first published his findings, while Joseph Henry was credited with self-inductance.
The ability of the other coil to experience mutual inductance when brought very close to an energized coil can further be proven mathematically using these equations here. Now, since the magnetic flux is proportional to I1, then epsilon 2 is equal to M21, di, all over dt. While for the first coil, it can be represented as epsilon 1 equal to M12, di2, all over dt, where the two mutual inductance, that is M21 and M12, are equal to each other, and the unit is in Henry. This can be called the mutual inductance coefficient. And that is it for today's series. I hope you have learned something new today. See you at the next one.